Okay, hi everybody, good afternoon. Many thanks for joining to our first Saphir regular webinar of 2024. And it is my pleasure to have with us Enrico Nardi, who will present about this X17 anomaly, status and prospects. So thank you very much, Enrico, for your time, and please go ahead with your talk.
Okay, thank you very much for inviting me because the topic I will describe is something that is under development here in Frascati. So it's an opportunity for me also to advertise what we are doing at the labs here at the Frascati National Labs. So the issue, just to focus on what will be the, if I can just change the page, here, okay, is it's an anomaly that is living with us since 8 years and has not been understood, has not been solved yet. And it is observed in nuclear physics processes. So the first time was observed in the decay of an excited state of beryllium-8, but the process that I will illustrate now is representative of also what has been observed with other nuclei. So there is a beam of protons that very, very well tuned energy that hits on a target of lithium-7 and excites a very specific level of beryllium-8. Most of the time, these excited states decays back into lithium-7 and a proton. And with a branching of order 10 to the -5, instead decays to the ground state of beryllium, emitting a photon. With a relative branching of about 10 to the -3, it emits a pair of it plus and minus through the emission of a virtual photon. So the 10 to the -3 is basically alpha divided 4 pi, and decays to the ground state. Now, of course, if you add something else, not only a photon, but something else that couples to the nucleus and to a plus and minus, it could also decay emitting this new state. And let's imagine that you have a boson, which I call X17, that the kinematic is such that the phase space is open to emit this boson. You could substitute this photon with an on-shell X17 that later decays in a plus and minus. In fact, this is what is the core of the anomaly. That an experiment in Hungary, the name is Atomki, has observed about 8 years ago the first anomaly, which basically it's a bump in the angular correlation of the plus and minus. Now, this is not difficult to understand. Imagine that I emit a massive boson. This massive boson has a certain boost. The boost depends on the energy that I have in the transition. So let's say how over the ground state I am, and the mass of the object. If the object decays to body, in its center of mass, in the rest frame, it decays back to back. If it is boosted, you will see that the two body acquire an angle which is different from 180 degrees. From the angle, you can, and knowing the energy that you have at your disposal, you can reconstruct the mass. You can say, okay, I have produced an object of this mass. Everything is consistent with a mass of 17 MeV. A boson that decays in a plus and minus. Now we'll give a summary of all these anomalies. So the first anomaly was observed in beryllium-8, state 18.15 MeV. Each time you will see this energy, it means how above ground state. So it is what you have at your disposal to produce a boson and to boost it to some extent. It was again observed again in beryllium-8, but in a different level at 17.63 in 2017. In 2018, it was confirmed the result of beryllium-8 with a different experimental setup, and a first hint of a similar anomaly in an excited state of helium-4 at 21 MeV was reported. In 2019, the anomaly in helium-4 was confirmed with a very high statistical significance. And it was shown that kinematically it was again consistent with an object of 17 MeV. So this we start focusing on the important message that if I have 18 MeV, I have a certain boost, and then I have a certain angle. If I have a larger energy, like in helium, then I have a larger boost, and the angle closes up. In 2021, it was observed the same type of anomaly in carbon-12. And since here you have only 17.2 MeV, you are more close to the situation where the boson is emitted at the rest, and so the angle opens up at 160 degrees. Finally, in 2022, there was a confirmation of this excess with a high statistical significance, and it was reported that the angles were consistently between 155 and 160. Some theoretical papers. So in December 2022, there was the Barducci-Toni paper that was trying to analyze the possibility that the boson is a vector, an axial vector, a scalar or a pseudoscalar, and concluded that axial vector interpretation is favored. In April 2023, so 1 year ago, we had a half-day workshop on the X17 saga here in Rome, and it was reported that the anomaly was observed in what is called the giant dipole resonance. So if every nucleus can be excited in a mode where the neutron and the proton oscillate against, the two clouds oscillate one against the other, this is called the giant dipole resonance. And in the decay of this resonance, again, the anomaly was observed. I will go in more details about all this information I'm giving now. Another theoretical paper from a theorist from Brookhaven and another theorist from CERN fitted all the data, giving a number very precise for the mass, and also values for the coupling to proton, neutron, and electron, range of value. Hoster and Pospelov produced a very interesting paper in June 2023, so about 1 year ago, claiming that data from pi decays into electron and electron neutrino were sufficient to rule out a vector boson nature. In August, this first hint of the observation of the anomaly in the giant dipole resonance was confirmed and was published on the archives. The only marginally different, I say marginally, I will explain why, different confirmation of the experimental anomaly came in August 2023 from a group in Hanoi in Vietnam. And it was reported in a talk. Now, it was not completely independent because there was a strong collaboration between the Vietnamese group and the spokesperson of Atomki. Initially, they even borrowed the spectrometer from the Hungarian group. Then they built up their own spectrometer. But in any case, I don't know to what extent. For example, I don't know if they had their own target built up in Hanoi or if they were using a target that the Hungarian gave to them. This would be interesting to understand. In August 2023, there was another important paper that it was a theoretical investigation of the process. When nuclear physicists say ab initio, it means they are not using modeling, but really the first principle. The conclusion was that this bump that was observed in beryllium could not be explained by standard model processes. Now, the apparatus, so you have this beam of protons, you have the target, the excited nucleus, and then initially they had 5 telescopes to detect the plus and minus pair. Then during the years, they have improved the experimental setup, they changed the accelerator, detectors, the electronics. For example, for helium, they used an arrangement with 6 telescopes. So this means that at least certain type of systematic effect should not be responsible of the effect because of this changing of the experimental apparatus. What do they measure? They measure the energy sum and the energy difference of the E plus E minus pairs and the angular correlation, so this angle theta. These are the data that they publish and that they interpret. Now, let's study beryllium a bit. So these are all the, not all the levels, there are many more, but the 2 important levels are these one, the green one and the blue one. They both are 1 plus, JP 1 plus, and the transition for both is to the ground state, which is JP 0 plus, and is isoscalar. The only difference between these 2 levels is that the level at lowest energy is an isotriplet level, and the one at higher energy is an isoscalar. For the rest, is the same type of transition. How does the transition proceed? There are basically 2 channels. One is through the resonance. So you excite an excited state of beryllium or carbon or helium, depend what is the specific nucleus, and then you have a decay. This is called resonant transition and proceed to a magnetic dipole operator. And then you have the radiative capture, which means you simply capture a proton on lithium without going through an excited state, and you emit a photon. You emit a photon, and you can emit also a boson, or you can emit it in plus and minus pairs. And this goes through an electric dipole operator. Everything which is valid for the photon is also valid for X17 of a vector nature. You can map the form factors. Is not the same if it is an axial vector or if it is a pseudoscalar, for example. But for a vector, there is really a one-to-one connection between the form factors of the massive particle and of the photon. So here is a sketch of how is the experimental and theoretical situation. So the blue line is the magnetic dipole, and you can see the 2 resonances, the 2 peaks. The green is the electric dipole that doesn't go to a resonance, so it is flat. And of course, what you observe is the sum of the 2. So you might have a certain contamination, of the direct capture, for which you don't have a specific quantum numbers of the resonance state as you have for the magnetic transition. So this was the plot of the first data published. You see, they used the 4 types of energies for the proton hitting the target. So the lowest energy does not excite the resonance. The 2 in the middles, they manage to excite, and the other one is too high energy, does not excite. This is the bump that was first observed around 140 degrees in the angular correlation. So this counts the number of events as a function of the angle. You see that below resonance and above resonance, everything is smooth. But when you can excite that specific resonance, you have this bump. And this is a similar bump that was observed in the invariant mass. So in plus and minus, you measure the energy, you construct the invariant mass, and you have an excess of counting with respect to a smooth decrease in background around here, 17 MeV. So the simple interpretation of this is, okay, I have produced a 17 MeV mass boson. This is the initial result for the other excited state at 17.6 MeV. And Atomic reported that they didn't notice any similar effect in the case of this specific level. However, soon after these results were published, the group of Feng in Irvine published a paper trying to interpret the result, and they noticed that although one state is isoscalar, the other is isotriplet, you have a very strong isospin mixing. So they concluded that if they had observed a resonance in the resonance here in the 18.15 MeV isoscalar level, they should have observed also in the 17.6, except for the fact that here you have less energy, so you have some phase space suppression. They reproduce again the experimental setup. They measured with a higher statistical accuracy the decay of the 17.6 fluor, and Atomic found this excess, as was predicted by the theoretical group of Feng. The bump location also is significant. It moved at a slightly larger value, as you would expect if the boost is a little bit smaller than from the other state. This we skip. Standard model explanation. So of course, already in 2017, people start seeing, trying to understand if this anomaly could be explained by the standard model. The situation was a bit confused. There was no agreement. You had studies that report, we find that the model improvements. So you can model whatever and try to improve the fit to the data, but cannot explain the anomaly. The process does not give a satisfying explanation. Other people claimed that the structure seen by Atomic could be reproduced in the standard model, but nothing was conclusive. And keep in mind that all the studies listed here are using some modeling, some nuclear physics model to try to see what happens in the decay of the resonance. 1 year, less than 1 year ago, there was a paper that studying instead ab initio the process proton on lithium initial state, ground state beryllium, E plus E minus final state, putting inside everything. No? The magnetic dipole, magnetic quadrupole, electron dipole. So very serious, a very complete study for what I can understand, not being a nuclear physicist. The conclusion was that they can reproduce the background in the plus and minus angular correlation without the bump. So the bump seen in the data, if real, cannot be explained by a standard model electromagnetic process. About particle interpretation. So a set of constraints come from the quantum numbers. So the beryllium excited state is 1 plus. The ground state is 0 plus. If you emit a scalar, which is also 0 plus, then you have to emit in a quantum state of angular momentum 1. And then the parity is -1 to the 1, so it's -1. And so the scalar cannot explain the transition. It would go to 0 minus, not to 0 plus. Other constraints come from atomic parity violation in case the boson has not well-defined parity, because it will give a signal. In other models, popular models are excluded because of other constraints, and in particular, the B minus L vector boson is excluded, and a kinetically mixed dark photon is also excluded. Now, there is something peculiar about this object, that it must be to some extent protophobic. Protophobia comes from pion phobia, and the point is that we have a very constraining limit from Na 48 to from non-observation of pi 0 to photon and missing energy. Now, this decay proceeded through an anomalous diagram, where here you have a photon, so you have the charge of the quarks that go around the loop, and here you have a dark photon, and so you have the coupling of the quark to the dark photon. Now the charge of the up quark is 2, the charge of the down is -1, but you have a minus here because the pi, the isospin is the neutral component of the isospin triplet. In the end, what you constrain from non-observing this process is this combination of coupling. 2 is the charge of the up, coupling of the up to the boson, 1, the charge of the down, and coupling of the down to the boson. Now, this is exactly the same combination that that enters in the proton. So if this number is small, and small with respect to what? To what you need to explain the signal that has been observed. So the signal that has been observed from beryllium has the same number of proton and neutron, 4 and 4, so has the same number of up and down quarks. So the signal is explaining by a certain value for this combination, which is a bit large with respect to this. This means that there should be some kind of tuned cancellation between the coupling. And since the coupling of the proton is also 2 epsilon up plus epsilon down, at the level of 10%, this combination should be 0. So, in resuming, pion phobia is suggesting that this object should couple weakly to the proton and much more strongly to the neutron. So here are some numbers of value of the couplings, and also to the electron, to explain the anomaly. Now, open current limits, of course, you have other constraints from other experiments, like Na 64. This was relatively recent in 2020. They close various regions. This red line is 16.7 MeV. I drew it when it was the first indication. Now the mass, the fit to the mass, the best one is a bit above 17. So this line is a bit on the right. You have a window open, which is not excluded by any other experiment. Now let's go to helium. So Atomki changed the nucleus, and they used tritium, a proton hits tritium excite some level of helium. It excites simultaneously 2 levels, because these are, you see, there is a large overlap. The level at 20.21 and the level at 21 MeV. So when you shoot here, you know, at this energy, you don't know which one you have excited. Initial data showed a very sharp peak. Then the second run, shooting mainly on the 2021 here, but also you still have a portion of the tail of the 0 minus peak that can be excited. And again, they see these bumps in the angular correlation. Now, these bumps you see are a smaller angle, no, let's say 120. And the energy in the game is larger, so the boost is larger. So kinematically, it is consistent. In 21, there was helium is a bit more simple than beryllium as a nucleus. So there was a paper doing an ab initio study of the process, and the conclusion, I go a bit too fast, was that helium anomaly cannot be explained by standard model physics. Now, let's put together beryllium and helium. There is a theoretical value for the angular correlation is around 112 degrees for helium, 139 for beryllium. And this is again another paper of the Irvine group, and 161 in case they have had used carbon-12 at the excited level 17.23. So here the energy is small and you are approaching 180 like for boson emitted almost at rest. The data indicate these masses consistently around 17, and they match very well the angles. And also the carbon that was a prediction is matched by the most recent data results from atomic. Here you can see a picture. So here you have different masses. The curves, the black lines are different masses. And you have the two helium levels, you have the two beryllium levels, and the carbon level. This is anticipated from what I will say now in the following slide. And they all nicely sit on the 17 MeV curve. So this means the three processes are kinematically consistent. It's more than three, in fact, because you have two beryllium. This is carbon. For carbon, they use proton hitting boron 11, excite carbon-12 at 17.23 MeV, and observe the correlation in the plus and minus decay products. They use four different energy for the proton. When they excite the resonance, they see the bump around 160, 65. Now, second issue is, okay, kinematically, all these observations are consistent, I would say in an impressive way. It's difficult to think what type of systematics could mimic such a behavior. But you can ask, there is dynamical consistency. The first step is a study of selection rules. And here is already informative because a scalar is excluded, this I said at the beginning. A pseudoscalar cannot explain carbon-12. So it's disfavored. The only possibility are vector and axial vector. They can explain beryllium, carbon, and helium. Also, helium axial vector can mediate the transition from the level at 21 MeV, and vector can mediate the transition from the level at 20.2 MeV. But there is more because you have measurement of branching ratio. So you can ask, if I'm observing carbon a certain branching ratio, I derive some coupling. Then I put this coupling in the case of helium or in the case of beryllium. Do I get the branching ratio that I have observed? And the answer is yes, to some extent, yes. There is a region where consistently you have the same couplings to proton and to neutron that can match what you observe in beryllium-8, in helium-4, and carbon-12. Now, this is just a suggestion. I had a chat with Attila, which is the spokesperson of Atomki. I say, well, you might want, so they use this level that can be consistent if the transition is mediated by scalar vector and axial vector. Why don't you try to excite this or this state? Because here the transition can be mediated just by scalar and vector, but we know scalar is excluded by beryllium. And here by pseudoscalar and axial vector. So if you measure these two, then the nature of the object should be identified. Unfortunately, the point is that they are using targets that are too thick, and so a bit of a loss of energy in the target will drive them out the resonance when the resonance is so small, no? 96 keV, 42 keV. While for the original measurement, they used 1 MeV width, an excited state of a width of more than 1 MeV. However, were planning, this was a private communication, to try to make a thinner target so that the energy loss would remain below 30 keV, and then they might try to investigate these two excited states. Summarizing, so the three anomalies are all more than 6 sigma, so they are not, cannot be interpreted as statistical fluctuations. They are bumps, not general flat or almost flat excesses, not a single beam or a last beam effect. If you introduce a new particle, you improve the fits to the free nuclei. The standard model explanation are really strongly disfavored. At this point, I would say, after the paper on beryllium may be ruled out. There is kinematic and dynamic consistency for a vector and an axial vector. And then the carbon was a prediction. Now, I will not go through all the models that have been proposed to try to explain this observation. Many attempts tried also to build connection with dark matter, with the G-2 of the muon. There are at least a couple of dozen of models. But I will give my opinion about this situation. And I will use 3 aphorisms. The first one is due to Sir Arthur Eddington, that once said, never trust an experimental result until it has been confirmed by theory. Now, do we need X17 for a better understanding of fundamental physics? To understand dark matter, to understand, I don't know, granulification? The answer is clear, no. We don't need. This doesn't help to solve the fundamental problem, neutrino masses of the standard model. However, a similar situation happened already in 1936. So in cosmic ray showers, Anderson and Edermeyer observed charged particles with a mass around 100 MeV, and they were first interpreted as the mediator of nuclear forces, because the range of nuclear forces matches a mass of a bit more than 100 MeV. We know it matches the mass of the pions. But soon it was understood that this particle did not have any strong interaction. And they were like heavy electrons with no role in nuclear interaction. This seems surprising, incongruous, and led Isdor Rabi to exclaim, who ordered that? The muon. like now, who ordered the X17? And now we know that the muon was the first discovered, or a threefold replica of electron up and down. So it opened up fermion family replication. And finally, Carl Sagan once said extraordinary claims require extraordinary evidences. And in the last part of the talk, I will show how in Frascati we might be able to provide this evidence if it is real, the existence of this particle. Here I will not go through because time is passing quickly, but I would just mention that these are experimental perspective. MER2 at PSI has already been taking data. Data are under analysis. They are trying to reproduce the beryllium experiment. So excite beryllium and observe the plus and minus. Montreal also want to try to reproduce beryllium. It seems they are ready. They say it should take place in early 2023. I have no news if in fact 1 year ago they took data. Luna and neutron time of flight at CERN, they concentrate of helium, not on beryllium. There is, however, only one mentioned experiment that is trying to use particle physics to see if the X17 exists or not. Note, all these experiments are nuclear physics, only the last one. They published in January, 1 year, a bit more than a year ago, a paper saying they are ready to run, but I know from the JLab scientific committee that they will not have the beam before 2025. So this experiment will be delayed. Validation. Already in 2017, I heard about this anomaly at CERN from a talk of Jonathan Feng. And then I thought, okay, if the X17 particle decays in plus and minus, then I plus and minus can annihilate in X17. And at Frascati, we have a LINAC. It's not a very powerful machine. It can produce positrons from 150 to 500 MeV. But if you try to see what does it mean this when they annihilate of electrons in a target at rest, they cover the range in square root of s between 12 and 22 MeV. So 17 is right in the middle and correspond to an energy of the beam of 285 MeV in the middle here. So this is clear. At this point, you say, well, I have to convince people of the beam time beam test facility in Frascati to tune the positron beam to that energy, and I have to convince the people of PubMed that have a detector to try to detect the production of this prime. There is a good point in favor of this program that the resonant production is enhanced by order of magnitudes with respect to Bremsstrahlung. You see, this is the number of bosons produced as a function of the mass. So Bremsstrahlung, you are here, associate production, which is the analogous of a plus and minus that go into two photons. Just you take a photon and you replace with a dark photon. You are here, but with resonant production, you have 10,000, 1,000 more events. Now, this program has went through the experiment. PubMed is a positron annihilation for dark matter experiment. This experiment was planned for a different type of measurement. They had to measure single photons from associate production. So was not very well suited to detect E plus E minus pairs from decay of a boson. But experimentalists here are really exceptional in adapting the detector. And about a bit more than 1 year ago, 43 points were taken in the senior region, and control points just to see what is the background. Here you are away from the resonance, from the hypothetical resonance. So if you measure background here, then you have an handle on the background in the senior region. So the point has been taken. Now, our colleagues are proceeding with the blind analysis, and this was the initial projection of that was carried out with some experimental colleagues, and Luc Darmet, that was a theoretical postdoc here in Frascati. And we have seen with the statistics that was planned, we could exclude completely close up on Na64. So exclude the vector and axial vector nature of this hypothetical boson. It could not close the pseudoscalar hypothesis, but pseudoscalar do not explain carbon. So this is disfavored. Now, just 2 months ago, we discovered an effect that actually I knew about it, but I thought in the PADME target, which is diamond carbon of 100 micrometers, so a thin target of a low Z material, I thought it was not very relevant. In fact, it is relevant. And the fact is that electrons in a material are not at rest. They have a momentum, no? They are localized in space, and so they have a spreading momentum. And the spreading momentum means that you spread out in the collision the signal. So when you have a beam that hits of positron that hits an electron at rest, if you know the energy of the beam precisely, you know exactly also square root of S. But if the electron is moving, then you don't know anymore precisely square root of S, and you have a certain spread. So this effect is causing a certain loss of sensitivity. Now the projection we have is the orange line, no more the blue line. But it's already planned that next fall, more statistics will be taken to be sure that the object doesn't sit really in that little corner. Okay, these are projections. In fact, the data taken have already a bit more statistics. One surprise, we just published the past week a paper on this effect of electron movement in the target, because this will affect everything. Muon, which is an experiment, the JLab, the Poker, which is also another experiment at CERN. It's important. We have seen that if we instead use tungsten 5 centimeter, so tungsten have core electrons that are relativistic. And when the positron hits, it can hit head-on, and so the energy in the center of mass can be increased in an important way. And so with a beam that actually could reach 23 MeV maximum in the hypothesis the electrons are at rest, you can go up to 80. So we are now studying this effect because we would like to move this curve up and close this area. There are many effects going on here, but we are moving towards the idea of studying a target of uranium-92, which is the highest Z we can use, so the highest velocities. I mean, we want to use atoms as particle physics accelerator. This is the point. Oh, I have here just a plot of validation. So if the object is there, what do you expect to see? Well, in the limit of zero velocity, so in the static limit for electrons, you would have seen this bump. Beautiful bump for the coupling, which are, this should be -4, 3 to 10 to the -4. Now you can, I don't have the plot including the effect of velocity, but the bump is a bit, you can expect that it is a bit spread around. In any case, we just concluded this. We gave our equations, our procedure to the experimentalists. They were waiting to include this effect. The black box is still a black box, has not been opened yet, but it will be opened at the end of this month or beginning of May. And then we will see if we have just some limit or if we will have a nice surprise. And these are my conclusions. So 3 anomalies at least have been observed in nuclear transition. Statistical evidence is very strong. No standard model of higher order nuclear effect can explain consistently. The crucial point is that except for this confirmation from Hanoi, everything is coming from atomic, from a single experiment. And we need additional independent validation, as always when we find anomalies in some physics process. There is an intense effort of planning nuclear physics experiments, but it takes time. Mach 2 had some problem with the target. We had the velocities that delayed the analysis. What I think is that to be sure that there is something, or that something is ruled out, we need an experiment of completely different nature, not nuclear physics, but a particle physics experiment whose results can be directly compared with the hints from nuclear physics processes. So I guess that I'm sure that a particle physics experiment will be decisive to validate and disprove the X17 hypothesis. And I thank you very much for the attention. I acknowledge the postdoc that have been working with me on this topic, the PADME team, our experimentalists of the detector, and the team of the beam test facility in Frascati that managed to have to squeeze out the beam, to control the energy. They did really a great job to try to solve this puzzle of the X17. Thank you.
Thank you, Enrico, for this very comprehensive talk. I'm sure there are plenty of questions, comments.
Yeah, I have a question.
Yes.
Yeah.
Hi, Sergey.
Yeah, first of all, thank you very much for this really very interesting talk.
Thank you, Sergey.
Yeah. So my question is about the possibility that the particular experimental setup of atom-key collaboration, which is the only collaboration which observes this anomaly, could be, could mimic somehow this effect. I wonder if the atom-key collaboration or some other group analyze it, any possible origin, apparatus origin of this anomaly.
Is really it's difficult for me to answer this question because you see it is a systematic that is mimicking a single particle. So they see at least 3 anomalies. If you put also the giant dipole resonance, you see 4 anomalies. And these anomalies are at different angles, but always the same mass and are kinematically consistent. Now, I also want to be really nasty, to say, imagine that they are just cheating us. No? They are just inventing the data. For what I know from my interaction with the group, atomic group, they could easily cheat on the kinematics, because that's relativistic kinematics. But they would not be able to cheat on the dynamical consistency, because they are really nuclear physicist experimentalists. So altogether, this is very puzzling situation. I don't have any idea of what type of systematic could mimic this. I just want to see. You see, they are the only one that see it, but they are only the only one that have been able to do these experiments. The other have not reported null results. No, we are still waiting that other experiments will try to investigate the same process. And for the moment, we don't have results.
Yeah. Okay. Thank you. Thank
Yeah,
you.
well,
I have a remark. Hello. So I am Mikhail. I represent NA64, and actually it was me who made this analysis on the search for X17 and NA64.
oh, very good. Yes.
So the first remark is that I saw that last year there was a paper, there was a result from NA62 that apparently excludes pseudoscalar explanation. There was I didn't see this paper in your list of papers.
No, you didn't see because I stick to more to possibilities that can explain beryllium, helium, and carbon. Since pseudoscalar cannot explain carbon, I just say it's disfavored.
Okay.
Because we have anomaly in carbon, the anomaly is even more marked than in other. I mean, so it's not that I'm against the idea. I said, oh, in carbon is systematic, in helium and beryllium is physics, is a particle. No, if we want to take the hint as really a sensible hypothesis, then this X17 should explain also carbon. In that case, cannot be a pseudoscalar.
Okay, thanks a lot. Then next is that in an A64 we prepared the proposal to extend the search for X17 and cover the higher values of couplings.
Yeah, this is very interesting for me, and I'm happy you are here because I want to ask you, you see, how much you can go up here.
So there is a paper, this is published, and in this paper, if we have sufficient beam time, which is approximately 4 months of beam time, then we can cover in the vector case or axial vector. Then we can cover all remaining space here.
Up to Chloe?
Yes.
Okay. So 4 months and then maybe 1 year of data analysis, something like that.
Yes. Yes, approximately
Okay.
like this. But at CERN, well, apparently they are not very enthusiastic about giving us this beam time. I don't know, maybe they don't believe very much in this X17. So this is the problem, because we even have practically all subdetectors for this. So we don't need to make some new subdetectors. So this is about our proposal that probably should be listed in the possible ways. Or
yeah, if when approximately when was published the archive version.
Yeah, I can send you.
Okay. If you give me the number, so I will update my slides. I missed
yeah.
paper.
And finally, if there is a proposal to search for this particle in a fixed target experiment using the resonant annihilation process, we have a program, and we have a program to simulate such processes. And last year, we worked exactly on this question of moving atomic electrons.
Yeah, yes.
So now we have all these more or less ready. Well, hopefully there are no bugs here, but it is ready to simulate such process.
But it's not trivial at all. How do you simulate the electron motion?
We we looked inside the GEANT4 codes.
Yeah,
and we used approximately what is used there.
but Gen4 doesn't include the motion of atomic electrons.
It includes in the Compton scattering.
Right.
I'm
In
in
Compton
contact
scattering, I
with the
didn't look, but it must, because in fact what we used is what is called the Compton profile.
yeah,
Compton
I discussed
profile, it gives you information on the motion of the momentum
I discussed
distribution
it
of
with the authors of Jean-Paul, and then we made something similar in our program. I can also send you, it is published, the papers about this package, and I can
I
send
would be
you.
very interested, because we had a very hard time. This is solid state physics. We had to learn solid state physics to try to find a way to treat consistently the velocities. Let's say in this first paper, which is here, published in 2018, I found a way to include that using data from positron annihilation at rest. So you shoot positrons, they stop in material, and then they emit two photons, and the photons have a Doppler shift, which is caused by the motion of the electron. So from this Doppler shift, you can trace back the probability of annihilation when positron at rest as a function of the electron momentum, which is not the same what we need, because a positron at rest in the material is not a plane wave of a positron in a beam. It has a wave function that suffers distortions, but it was good enough. In this case, we did something more sophisticated. It was published the past week, the paper. We used the Compton profile, and we used also to study tungsten, we used also relativistic correction. So this paper, I think it can be very useful for fixed target experiments looking for resonant production.
Yeah.
But
So
I will be very happy to receive your information from your part. Very, very happy.
I will contact the organizers of the seminar, and I hope they will send me your contact, your email.
Yes, please, Michael. Thank you. This is excellent.
Okay, and again, thank you very much for this very extensive review of
I
this.
hope they will give you the beam. Look, my first proposal was here in 2017. Eventually, data were taken in 2022, so 5 years it took to convince experiments that there was a physics case. Of course, in the meanwhile, this anomaly came out in helium, then it came out in carbon, so people started being very puzzled and more interested. Eventually, we took the data, we have the data, but it was a long story. You have to. Initially, they said, of course, this does not exist. Who needs this? It's like the mu, no? But I hope you will have also the possibility to close up. It would be very nice if you could do that.
It is not so easy about the beam time, because there are many concurrents on this beam line, including us, because our baseline is to just to search for dark matter in missing energy events, which is a different, slightly different situation. So they
but going up here at larger coupling, I mean, the decay, for what I understand, the point is that at larger coupling, the decay occurs inside the dump. And this is the
exactly, this is the difficulty here. So for this reason, for this search, we increase the beam energy, and we make a very compact calorimeter.
You take okay. So you increase the boost.
Yes.
Okay.
Oh, this is described in our paper. I will send you the information.
Yeah.
I'll make sure you guys are in touch. So I'm sure you have plenty more to discuss, but in order to honor time, we have a few raised hands still. So perhaps we can move on. Thank you.
Please.
Alfonso.
Thank you very much, Enrico, for this very nice talk. I have a couple of questions. The first one is that the existence of a new boson coupling to the electron should modify some properties of the electron. For instance, G-2 of the electron. These couplings and the mass of the NX are consistent with the well-measured G-2 of the electron?
Well, the G-2 of the electron has a problem in itself. And the problem is that there was, you know that there are two measurements of alpha. The G-2 depends on the value of alpha that you put in. And one is from cesium and one is from rubidium. If you use the value from cesium, you get a prediction for the G-2 of the electron, which is something like 3 sigma below the experimental value. If you use a rubidium, you get another 2 or 3 sigma above the experimental value. So the situation of the G-2 of the electron is so uncertain that whatever contribution is doing this particle that has 17 MeV and has small couplings fits very well inside this at least 5 sigma uncertainty in the theoretical prediction. So it's correct what you say. There will be a contribution to the G-2 of the electron, but for the moment, the theoretical prediction is so uncertain due to these two different measurements of alpha QED that this object cannot be seen in that measurement.
Oh, okay. And my second question is, all the evidence for the X17 comes from measurement with light nuclei. I suppose that there is an experimental reason for that, the facilities, for instance. But,
well, I imagine you're right. I imagine that the fact is helium is 1 alpha particle. Beryllium is 2 alpha particle. Actually, beryllium is a molecular. Beryllium lifetime in the ground state is 10 to the minus 16 seconds. You know that there is no stable nuclei with atomic number 8. No? So beryllium is 2 alpha particles, very loosely bound, and carbon is 3 alpha particles. But carbon luckily is stable, otherwise we won't be here discussing the issue. So these are, I think, much more simple, closed shell, much more simple from the point of view of nuclear physics than open shells. I believe that's why they choose these 1 alpha, 2 alpha, 3 alpha nuclei.
But shouldn't it be interesting, for instance, try to search this effect in nickel, because nickel has a lot of stable isotopes, and to try to see if a varying number of neutrons can be seen in the anomaly.
Well, I guess that the issue is that when you have an experimental result, you want to confront with a theoretical prediction. And when you start having a lot of transition, excited states, multiples, interference between multiples, and the nuclear physics problem becomes so complicated that probably you don't trust completely the theoretical prediction. Even I told you, helium was done from ab initio approach 2-3 years ago. Beryllium was done 1 year ago, stimulated by X17. So I think the problem is really having a reliable prediction for what you expect from internal pair creation in the decay of this, that, or the other one excited state. And for a high Z material, I guess this problem becomes exponentially more difficult.
Okay, I see. Thank you.
You're welcome.
thanks. Maybe I can ask just one quick question, Enrico, concerning the future program at PADME, for example. I know that this action-like particle-like hypothesis is mostly disfavored, but if this particle it has a small mass, it could be produced in several decays of rare mesons. Maybe are there efforts to correlate some other type of measurements like lepton flavor violation decays, for example, to perhaps rule out completely this pseudoscalar hypothesis?
Well, of course, you're right. In fact, a very strong constraint comes from pion decays. Pion decays into a photon and something invisible.
Mm-hmm.
And this is what forces the what is called pion-phobic or nucleophobic, protophobic nature of this object. I have to say that I'm not aware about a fully consistent ultraviolet model that can accommodate such a protophobic vector. So it's just a phenomenological description, but you don't have a Lagrangian, no, from the beginning, no? And other decays, kaon decays, don't seem to be able to give constraint in such a way that this is excluded. The paper of Pospelov that I cited at the beginning was interesting because he is analyzing the case of the vector particle that couples to non-conserved current. He argues that this is the only possibility. And then he's using charged pion decays, no pi plus that goes in positron plus X17, and he shows that the limit from non-observation of the type of decay are sufficient to exclude the vector case for the X17. But other people with whom I've been talking, they say yes, but he has some theoretical assumption in deriving this result. And this theoretical assumption maybe could be circumvented or could be violated in some model. So it's not clear to me what is the situation for the vector. If you believe this paper is a beautiful paper, eh? If you believe it, then we are left with the axial vector. That's the preferred nature of the X17.
I see. Okay, thank you very much again, Enrico, for this very exciting talk and trigger a lot of discussion. So thank you so much. And I remind people to stay tuned for our next webinar that will be held on 10th of May. So thank you.
Thank you, Joanna, for invitation. Thank you to everyone that has been following the seminar. And I remain eager to get the information from the NA64 experimental. Okay, thank you.
Okay, thank you.
Thank you.
Bye bye.
Bye-bye.
Bye.